talk about some techniques for the pre-processing. I will talk about some techniques for in-processing. In-processing, mostly in machine learning, is fairness learning subject to constraint. So in machine learning, we have the optimization, and we want to have fairness as a constraint. You learn throughout this week that this deep learning is also optimization. So we want to maximize a certain function or minimize a certain function. So we want to, for example, maximize accuracy, and the function is accuracy. Or we want to minimize the error. So based on the tool that we are using, it's ranking or classification, the function is different. So anyhow, we have this optimization problem. So the goal of the optimization problem is a one metric, which is, for example, the performance of the system, and we want to optimize for that. But fairness is also another metric that we can add to the system and optimize for fairness as well. But we have to note that the optimization technique that I'm talking about is a general term. So for each machine learning that we are using, there is a different optimization problem. These optimization problems, they have different properties. So some of them are easier to solve, some of them are harder, but there are approximations for them. Some of them are hard, but there are some structure that we can actually use to solve them. Adding fairness, it's not easy, because it can actually change the properties of the optimization. So a simple optimization problem in the machine learning can actually go to very, very hard, become very, very hard, and we have to come up with a solution for it. So it's not that what I'm saying is that we can add fairness as a constraint. It's not as easy as adding a constraint, because it can change the property of the optimization. I will show you two examples of my own work of like how I add constraint, like fairness constraint, and it actually changed the optimization. The first one is that I wanted to make fair naive Bayes. Naive Bayes is the simplest machine learning techniques. If you want to solve naive Bayes, the closed form, and it's a convex optimization problem. I defined fairness as a degree of discrimination. Degree of discrimination is, this is a definition which is really strong. It is between group fairness and individual fairness, because I'm not just caring about like the population of female and male, but just all combinations of like adding the sensitive and non-sensitive. So I'm just comparing all these populations, subpopulations, which are exponentially many. And I'm searching through the learned model in order to see if there is any discrimination. So I'm solving it with the cutting plane idea. So I'm just extracting discrimination, adding it as a constraint, and solving it again. The thing is, when I'm doing it, this fairness constraint when I'm adding to the problem, I have to solve it as a signomial program. It's not a convex optimization problem anymore. Another example is that I define fairness in a relational context, because most of the work in machine learning is based on the classification and tabular data. But I work on the relational context. For example, if in the case of hiring, we have, in the case of promotion, the promotion is happening, for example, based on the feedback that you're getting from your manager. There is a relation actually happening here that the discrimination in the relation can influence on you getting a promotion or not. It's not just about your label, which is gender, right? So I worked on the probabilistic graphical model. I'm not talking about it here, but I worked on the graphical model. And in graphical model, the inference was convex optimization problem. So I wanted to add a fairness constraint, and I chose demographic parity because it's a legalized metric, and also inference is not learning. So I couldn't actually use, for example, equalized odds or equalized opportunity. And I added to the map inference, but adding it to the map inference was not working because the fairness constraint was not linear, so I had to approximate the fairness constraint to add it. So I had to do something to change it, and then added it to the optimization. So what I'm saying here is that it's not as easy as adding the fairness constraint to optimization problem. For each machine learning techniques, you have to come up with a solution, and there are so many papers actually talking about it, like how you can do it in deep learning, how you can do it in other machine learning techniques.